We'll get started in just a second. Again, a reminder, keep the videos off and all that good stuff. We'll get started. Okay, we'll get started in just a minute. Give everybody a chance to come in. Again, a reminder, if you have questions, you could use the chat box to ask those questions. And again, just make sure you keep your videos off. I appreciate it. Okay, so what we're going to do today, like I mentioned last time, is we're just going to lecture for a little bit. We won't go, obviously, the whole time and all that. You take a little break and then obviously get ready to take the exam, which again will be today. It will open up at 12 o'clock, which is our normal lab time, and you can take it. So we're just going to get through the rest of this chapter, maybe talk a little bit about the next chapters a little bit. And then again, like I said, we'll kind of stop a little bit early today, and then you could get yourself prepared to take the exam, which will again open up at 12. So we're just going to continue lecturing right now, and towards the end of this, we'll just kind of talk about, again, the exam and what you need to do, just to kind of clarify some points, and we'll take care of that towards the end. Okay, so we've been talking about types of reactions and different ways to classify reactions. So remember that when we look at a reaction, there's really three sort of driving forces, as we see on the screen here, as to what wants to make a reaction take place. The first one is, as we see here, it is the formation of a solid, which, as we talked a little bit at the beginning of this chapter, is really a precipitation reaction. So when we do form a solid as a result of basically mixing a couple of solutions together, that will form us a precipitate, and that is basically a precipitation reaction. As we talked about in the last couple of lectures, that type of reaction usually is also, as we'll see, what is known as a double displacement reaction. And a double displacement reaction, as we'll see, and as we talked about before, is essentially when you have two ionic compounds together. And basically what happens is the positive ion in the first ionic compound will switch partners with the positive guy in the second ionic compound. And what it does is it creates two new ionic compounds, usually on the product side. The result of that may result in a solid being formed based on something else that we also talked about, which was solubility rules, right? So it's those solubility rules that basically help us decide or determine if we put together these two ions, will they make a solid, or would we expect basically a solution to form? And those are the two sort of symbols that we typically can get from the solubility rules. Again, if something is soluble, it is what will get that aqueous symbol. And based on the solubility rules, if they are insoluble, those are the guys that are going to form the solid, and we'll get that solid symbol that's there. So that's one sort of driving force for a reaction to take place, is that formation of a solid. Another one that we also saw last time as well, which is also oftentimes not always, but oftentimes a double displacement reaction as well, is the formation of water. And we saw that happen when we looked at a acid-base reaction, right? So if we looked at the acid-base neutralization reactions that we looked at the end there, it basically will form two things, and one of the things that it forms is basically H2O, which is that formation of water, and then again, the acid-base reaction will also form a salt. So when you mix a strong acid and strong base together, like we talked about last time, those are typically the two things that you get is you get water and a salt. And if you also remember, what we talked about was the water basically comes from the H plus from the acid and the OH minus from the base part. So that's essentially where the water is formed from. The remaining part of those guys basically will end up as the salt, and that will be, again, just an ionic compound. And the last sort of thing that we talked about, I think, towards the end last time was this here, this thing, which is a transfer of electrons. And a transfer of electrons usually occurs in a particular type of reaction that we talked about, I think, towards the very, very end, which are known as redox reactions. And a redox reaction basically means a oxidation and reduction reaction that occurs. And when we have an oxidation reduction reaction, they always happen together. So what I mean by that is if something is getting oxidized, that means something has to be reduced. So they kind of go together. So the nice thing about that is as well, if you could just figure out what is either being oxidized or what is being reduced, you'll know by default the opposite is happening to the other species. And the definition really that you come across most often in this type of class in terms of oxidation is basically the loss of electrons, while the reduction is the opposite of that. So essentially what happens here is somebody loses electrons and somebody gains electrons, and the reduction reaction is when somebody basically will gain an electron. And again, there's a couple ways sometimes people remember that is Leo the lion goes grr. Again, loss of electrons, oxidation, gaining of electrons, reduction, right? Don't push. And again, sometimes people remember the oil rig as another way of doing that. And oxidizing is losing, reducing is gaining. So those are a couple ways that sometimes people will remember sort of a redox reaction. And when we talk about a redox reaction, we can oftentimes see it in terms of an equation. If we have something, for example, A goes to A plus plus an electron. The electron on the product side represents an oxidation reaction. This is sometimes called an oxidation half reaction. And that means like the electron is being lost, is being given off. So you typically will find it on your product side. And that's opposite when you have something, for example, what's a different letter? E, an electron plus AB will make B minus. And here the electron is on the reactant side. And that is typically the reduction half reaction. Like the electron is being gained, so it's on the reactant side. And they're called half reactions because essentially if you add these together, these two reactions, and you cross out the electrons on opposite sides of the arrow, you get basically the overall reaction is taking place. Any questions on sort of those things that we talked about previously? Now, the other thing that we also talked about as well is that there are many different ways that you could classify kind of the same reaction. And we've kind of come across it a little bit previously in this lecture, talking about different ways to classify really the same reaction. So let's take a look at some of these different classifications of kind of the same reaction. And this is the one that we were seeing earlier on the bottom here. Again, if we take something like our potassium chromate and mix it with our barium nitrate, this is really a double displacement reaction. This is a positive guy and a negative guy. This guy is positive, this guy is negative. So again, what's happening is our potassium is switching partners and coming up with our nitrate. Our barium then would come over here to our chromate and come together. And that is how we get our guys on the other side. And this is again also classified as a precipitation reaction, because based on our solubility rules that we saw earlier, if we put barium and the chromate together, we will get something that's a solid that's formed. And that's why, again, this is oftentimes referred to as a precipitation reaction, and can also be really a double displacement reaction. So if you remember that the double displacement reaction is essentially kind of the big umbrella, and the double displacement reaction is the big umbrella under which other types of ways to classify reactions. So a double displacement reaction oftentimes is a precipitation reaction, like what we see on the bottom of the screen here. And as we saw last time as well, it also could be a acid-base reaction, neutralization reaction. So again, kind of the big category of reactions is double displacement, and sometimes people will just use double displacement as a way to classify it, but a more specific way of classifying a specific type of double displacement reaction can oftentimes be a precipitation reaction, or it can be classified as a acid-base reaction. Any questions on that there? So as we were been talking about and sort of jumped a little bit ahead last time or a couple of days ago when we were lecturing, again, this is really what is referred to as a double displacement reaction. And this is down here is the generic way that you can always sort of recognize a double displacement reaction. And again, our positive and negative guy and our positive and negative guy. So typically whenever you start with two ionic compounds, you pretty much can expect this double displacement reaction to happen. And as we can see here, our A started out with B, but ended up with the opposite guy there, and our D, which is again a new ionic compound that's been formed. And same thing, our C here ended up with our B, making also a new ionic compound that is being formed. And again, this is the big sort of way to classify this type of reaction. If one of these guys over here on the product side makes a solid, then you could kind of further classify it as a precipitation reaction as well. So technically speaking, this reaction up on top that we saw, it is correct to classify it as double displacement. It is also correct to classify it as a precipitation reaction because it did form a solid. It would not be correct to classify this one as an acid-base reaction. Again, it's not really an acid-base neutralization reaction, as there's no acid or base basically involved. Any questions on that? Again, if you do have questions, feel free to type them in the box there. This also, again, is a acid-base neutralization reaction that we saw earlier. And in this reaction, we have a strong acid, which is right here, hydrochloric acid, right, which you should know how to name, especially in about an hour and a half, right? So, plus potassium hydroxide. So this is a strong acid and a strong base. And as we talked about, it really also is a double displacement reaction, positive, negative guy, positive, negative guy. And as I mentioned before, that's essentially where water comes from. It comes from, again, it comes from the H plus here, from the acid, and the OH minus from the base when they come together. And again, when they come together, that is basically what forms our water on this side. And our salt over here is made from the other two ions that are present, the potassium and the chloride, that come together to make the potassium chloride. So this is best probably usually in most cases classified as an acid-base neutralization reaction. Again, it still falls under that umbrella of double displacement reactions, which is technically a way to classify this. But probably 9 times out of 10, if somebody would classify this type of reaction, because it's definitely an acid and base involved, they would classify it as an acid-base neutralization reaction. So these reactions as well are typically the ones, when we talk about our acid-base reactions, our double displacement reactions, for example, that we can write the different types of reactions that we also talked about. Again, you can take this reaction that we have above and write the total ionic equation, which in this case, it would be H plus, because it's a strong acid, plus Cl minus, plus our potassium hydroxide, which will also break apart into K plus and OH minus, because it's a strong base, a strong electrolyte. Remember that we would not break apart something like water, which is a liquid. So when we do this type of reactions, we keep together anything that has a liquid symbol or a solid symbol is typically what we keep together. And then our potassium chloride, which is an electrolyte, will also break apart into its ions. And remember that this is what is referred to as a total ionic equation. Our complete ionic equation is sometimes referred to. And when we write this equation, it basically represents what's happening in the solution. In the solution, we pretty much got all these ions floating around. And we also will have some ions that are what are referred to as spectator ions. And those are the guys that we see on, again, both sides of the arrow that look exactly the same. So in this case, it is the potassium and it is the chloride that are your spectator ions. And again, we typically will cancel those guys out. And what we're left with is the last type of reaction or equation that we talked about, which is known as the net ionic equation. And what we're left with in the above is H plus OH minus makes H2O. And as we talked about last time, no matter what combination of strong acid or strong base that you put together, if you go through all three of those equations, the molecular equation, which is the one at the very top that we started with, the total ionic equation, and the net ionic equation, you will always end up in the same place when you take a strong acid and strong base. Basically, the actual reaction that is happening is the formation of water, which is why on that previous slide, one of the driving forces for a reaction to take place is the formation of water. And this is pretty much what happens with most strong acids and strong bases when they come together. Any questions on any part of that there? So again, this is a double displacement reaction, sort of the big umbrella. A more specific way to classify this reaction would probably be an acid-base neutralization reaction. Again, it's sometimes called a neutralization reaction because essentially we form water here. So let's take a look at some more ways to classify reactions. And really what we're looking at here is what we were talking about at the very end last time, which are these redox reactions. And again, the big umbrella, much like double displacement, is redox reactions. And under these redox reactions, we will see several different ways to classify a reaction. And it's sort of a different name, but it's still ultimately a redox reaction that's happening. And that's what's happening, say, for example, up here. Lithium here, when it starts, has no charge. Fluorine, that's naturally how fluorine comes, which means it has no charge as well. Remember, things don't get charges until they basically combine. So when a metal and a non-metal come together, that is when we get something that has a charge, and that's when lithium basically will get the +1 charge. The fluorine will end up with the -1 charge at that point. So again, by themselves, uncombined, how they naturally come, they will not have any type of charge, but when they do come together, they do get a charge. And by looking really at what happens with these guys, and another thing that we talked about in terms of sort of an easy way to perhaps figure out, what is being oxidized and what is being reduced, is by using just a basic number line. Again, when things get oxidized, they become more positive because they have lost electrons, so they have more protons than electrons, and that is when oxidation occurs. And when things become more negative, heading in that direction, that is when things gain electrons, our reduction occurs. And again, because they gain electrons, they have more negative than positive, so they become negatively charged. So we could use something like this number line and looking at sort of the differences in the charges. And really, these are sometimes what are referred to as oxidation states, but we don't really get into that too much here. But if we look at the lithium again started at 0 and it ended at +1. So the way that you could do that is simply just go to the number line and you're starting at 0. And in this case, it ends at +1, which means it's going in this direction. And that should tell us that it is heading to the right and is being oxidized. So the lithium here is basically going through an oxidation reaction where the lithium will lose 1 electron each and will go through oxidation. And in this case, if you want to balance it, because of the equation, we would have 2 of them, each losing 1 electron each. Now, if we look at the fluorine, we could do basically the exact same thing with the fluorine. Good choice. And if we look at the fluorine here, when it started at 0. And it ended at -1. And you can do the exact same thing. You can start here at 0. And -1 would be in this direction, which tells you that it is going through reduction. And the fluorine is basically gaining electrons, which means you could write a reaction like 2 electrons plus the 2 fluorine, F2, gives you 2F minus, and this would be your reduction half reaction. Up here, this would be your oxidation half reaction. Any questions on how to determine what is being oxidized and what is being reduced? Okay, so another type of redox reaction that is classified typically in a different way is what we see on the bottom. This is what is known as a single replacement reaction, which is usually a redox reaction that's occurring. But the way that you could recognize a single replacement reaction is you typically have something by itself over here. So this is uncombined. Combined. No charge. So this could be a metal, for example. And we will have an ionic compound like this, something that's positive, negative. And basically what's going to happen in this case is if this was a metal to begin with, the metal does not have a charge to begin with, but when it does gain a charge, it would become positively charged. So it's going to come in and kick out the positive guy. And when it kicks out the positive guy, it will make a new ionic compound with the negative one that's there. And you will get the B in this case come out with no charge. So it's a very common reaction. It's known as a single replacement reaction. Something comes in, kicks out something else in an ionic compound, and a new ionic compound is formed. And then whatever got kicked out comes out over here with no charge. This reaction could also happen if what you're starting with is a nonmetal. So again, you'll have your ionic compound here. That's a positive and negative guy. You'll have this guy that has no charge and is a nonmetal. And what happens in this case is same thing. The nonmetal actually will come out and kick out the negative guy, because the nonmetal is starting with no charge, but when it gains a charge, it will become negative. So it will actually kick out the negative guy. And we'll end up with, again, a new ionic compound. The B and the A would come together, positive, negative, and that C would come out by itself with no charge. This reaction here is the exact reaction that we saw when we did those halogens in the test tubes in that experiment, where we had the different layers, and the halogen was coming in and kicking out. In order for this reaction to take place, whatever is coming in, so for example here, whatever is coming in needs to be more reactive than what it is replacing. So if this reaction did take place, this would mean that A is more reactive than B. If we did this reaction, did not see anything happen, then that would mean A is less reactive than B. So whatever is coming in this type of reaction has to be more reactive than what it's replacing. And if it is not, then the reaction actually will not take place. So if we look up here, you can kind of see the general profile, what we were just talking about. We have our metal here that is uncombined, has no charge. We have hydrochloric acid, which really is a positive and negative guy. So essentially what's going to happen here is the zinc's going to come in and it's going to kick out the hydrogen. When it does kick out the hydrogen, hydrogen comes out by itself in its natural form. And in its natural form, that's hydrogen gas. And you've done this reaction, I think, somewhere along the way. And what this is typically what you'll see, bubbles start to form. So you'll see a whole bunch of these bubbles, and that represents obviously the gas that has been formed. And then what we make over here on the other side is a new ionic compound, and that's the combination of the zinc that's coming in, which has now gained a charge, and the Cl minus, which is negatively charged. That would become together and make zinc chloride. Any questions on that? Okay, so a single replacement reaction always looks like this sort of setup. And again, it is basically under the big umbrella there of single replacement reactions. Another important type of reaction is one that's known as a combustion reaction. And usually when we talk about a combustion reaction is essentially an organic combustion reaction is usually what people think about. So usually it's an organic substance, and that basically means it has carbons, hydrogens, and oxygens, plus O2 will make CO2 plus water. So these are always the products that are always sort of formed in a combustion reaction that involves basically an organic one. So that's what we see here. This is methane, like when you light your Bunsen burner. Plus our O2 makes our CO2 and water. So those are always the products that you get in this type of reaction. Propane, which is C3H8, plus our O2 gives us our CO2 and water as well. So usually in a combustion reaction, that's usually the one most people are talking about, is the organic one. the more generic definition is basically for a combustion reaction, it pretty much just needs to have O2 involved in the reaction. So technically anything that has O2 could be classified as a combustion reaction, but pretty much 99% of the time, this is the type of combustion reaction that most people are thinking about. But really, technically speaking, if it has O2 on the reactant side, you kind of consider it a combustion reaction. So combustion reaction will always have this. The only time that it will not necessarily, in an organic combustion reaction, not have CO2 and water is in something known as what is sometimes referred to as a incomplete combustion. And in an incomplete combustion reaction, it's pretty much the same reaction. The only difference is instead of CO2 on the product side, you get carbon monoxide on the product side plus water. So this is why it's sometimes called an incomplete combustion, because it makes CO instead of CO2. But usually most combustion reactions will make a CO2 and water. Any questions on combustion reaction there? So a couple other types of ways to classify a reaction. Go back. And the first, this way is what is known as a combination or a synthesis reaction. And pretty much in a combination or synthesis reaction, much like the name implies, we're going to combine two things. So basically what that means is we have two things that essentially will make one thing. So two things come together, makes one thing. Again, is your combination, or a lot of people nowadays call it a synthesis reaction. And most combination or synthesis reactions are really still in that big umbrella of redox reactions as well. And when we look over here, this is essentially what we see. If we take our water, we have two things that make one thing, right? So they come together and make a combination. Here we have our sodium and our chlorine, two things that come together to make one thing. Again, also a combination or synthesis reaction. Again, if you look at the sodium chloride here, or this formation, it is most often probably called a synthesis reaction. Not sure why that's a B, that should be an N maybe. But it's also, again, a redox reaction that's happening. If we look at the sodium here by itself, it has no charge. If we look at the chlorine by itself, it has no charge. Again, they will gain charges when they come together. -1 for sodium because it's group 1, and minus 1 for chlorine because it's group 7, and +1 for sodium because it's group 1. And again, if you take your number line here, we see for our sodium is going from 0 to +1, which is in this direction, which means it's going through oxidation. And if we look at our chlorine, it's going from 0 to -1, which again is in that direction, which means it's going through reduction. And that typically is what happens when we take a metal and a non-metal together, like we talked about with naming, with bonding. Typically when this happens, we have an electron transfer that's happening. And again, the metal will become positively charged and the non-metal will become negatively charged. So probably the better classification, or most often classified these type of reactions here, would most likely be classified as a synthesis or combination reaction. But again, under the big umbrella, they're really also redox reactions that are taking place. Any questions on that? Okay, another type of reaction, which should be, I believe, the opposite of the one we just saw, is what is known as a decomposition reaction. Oops, come back. And in a decomposition reaction, it is basically the opposite of a synthesis reaction. In a decomposition reaction, we're taking one thing and making two or more things. So it's basically breaking down into two or more things. So a combination reaction is putting something together. A decomposition reaction is basically breaking something apart. They're kind of like opposites of each other. Combination, put it together. Decomposition, basically break it apart. So if we take our opposite reaction of our combination reaction, and we start with one thing, which is our water here, and we make two things, which is our hydrogen gas and oxygen gas. Again, two things make one thing, your classic sort of decomposition reaction. Another common one that you see a lot is H2CO3, which is carbonic acid. When that is formed, it typically will very quickly break apart to H2O plus CO2. And again, one thing makes two things is your decomposition reaction. Any questions on that there? So to sort of summarize the different types of reactions that we talked about, kind of the big type, double displacement. And again, under that sort of big heading, you could also classify a reaction, as we saw, as a precipitation reaction. And you could also acid base reactions kind of fall under there as well. And then we kind of have another big sort of heading, which are known as redox reactions, which are oxidation reduction reactions. And under those, we have things like our single replacement reactions. A lot of times our combination reactions, our synthesis. Also, our decomposition reactions a lot of times will fall under there because they're kind of the opposite. And again, combustion reaction will sort of fall underneath there as well. So again, as we talked about, many different ways you can classify the same reaction depending on sort of what aspect you're looking at. But there are these sort of big umbrellas, which there's other guys underneath that basically fall under there as different ways to classify it. A lot of times people will oftentimes focus on sort of the lower classifications for a reaction, but sometimes people will also just talk about it in terms of double displacement or redox, because basically both of those types of reactions, double displacement, redox reactions, cover those three driving forces for a reaction. And that is basically a precipitate being made, which would be your precipitation reaction, a transfer of electrons, which is ultimately your redox reaction, and the formation of water, which is really a lot of times your acid-base reaction, which is your double displacement reaction. Any questions on how to classify reactions? Again, you do need to know these classifications. You do need to be able to obviously recognize them. And as we talked about in this chapter, write the correct reactions and everything like that. Any questions on any of that? If I'm not mistaken, that should wrap this chapter, which is chapter 7. Yep. So I'm going to stop sharing for just a second. We're going to go to chapter, I think it's 9. So it should be a little bit of stoichiometry. So we'll just start a little bit of that before we cut off in about 20 minutes, I think. See if I could find that there. what I was grabbing there. I'm going to try that again. I apologize if you heard all the beeping. All right, give it the old college try here for a third time. All right, here. There we go. I think you should see that, I hope. Too many things to click on. All right. Any questions, though, before we begin on what we've been talking about in the last chapter? Again, this should be chapter 9. All right, so in this chapter, we're going to be kind of putting together several things from the last couple of chapters that we talked about. We're going to be putting together our grams to moles, which you should also know for today, I hope, in about an hour. And we're going to put together our balancing of equations. And what we're going to be able to do is basically put these two things together, and we're going to be able to do some calculations from equations. And these type of calculations that we do from these equations, this type of thing is what is known as stoichiometry. And it's an important type of calculation that we do a lot in chemistry to basically figure out certain things in a reaction. We can figure out how much product we would make. We could also figure out how much reactants we would start with if we know how much product we make. And we're able to really calculate in a reaction, looking at both the reactants and the products. We could calculate again if we just know one piece of information. So if we know one piece of info on the product side, we could figure out how much of the other product we made. We could also figure out how much of the reactants we started with, or again, if we know one piece of information on this side in terms of how much reactants we're starting with, we could figure out how much products we made. We could also figure out how much of the other reactants we actually had in that reaction. And all what we're going to be doing in this chapter, everything 100%, all starts with one very important thing. You need to have a balanced equation. So that equation that you use for these type of problems, and always, it does need to be balanced. Yeah. And if the equation is not balanced, then pretty much everything that you'll do will be wrong in terms of the calculation. So you always, in these problems, definitely from now on, if you haven't been, want to make sure it's balanced. And again, when we balance equations, it's those coefficients that we use in front. And if something is balanced, basically what that means is we have the same number of elements that we started with and that we finish with in terms of the reaction. Again, conservation of mass and everything. We don't lose anything along the way. If we start with 2 hydrogens, we should end with 2 hydrogens. 6 carbons we start with, we should also end with 6 carbons. Now, from a balanced equation, we could come up with several relationships that help us calculate these type of things. One thing we could say about those coefficients is that is how many molecules we have of each of these things. So for example, here, the 2 would tell us we have 2 molecules of H2 react with 1 molecule of O2 to form 2 molecules of H2O. Now, The relationship that we use the most here in this chapter and in stoichiometry is this relationship right here. This is what is sometimes referred to as the mole to mole relationship. And basically, it's the exact same thing as we just did above. It is actually the coefficient, no calculation needed. So the coefficient in front of the H2 is 2. So we could say there are 2 moles of H2. React with 1 mole of O2 gives us 2 moles of H2O. We also can look at that conservation of mass. If we started with 36 grams of reactants, we should end with 36 grams of products. And that is because what we start with and what we end up with in terms of the elements are exactly the same. So they have the exact same mass on the left-hand side of the arrow as they do on the right-hand side of the arrow. So we should have the exact same mass of reactants as we do products, so we don't lose anything. So this mole-to-mole relationship is important because it allows us to come up with relationships from the actual equation. And the relationships that we could come up with, for example, for the one that we're looking at, is we could say that there are 2 moles of H2. And for every 2 moles of H2 I throw in there, I need to also throw in there 1 mole of O2. And again, this comes from the coefficients in the balance equation, not doing any type of calculation, just looking at the balance equation. We could also say that for every 2 moles of H2 I throw in there, I could see on the product side, I get 2 moles of H2O out. I could also look at O2 and say that for every 1 mole of O2 I put in there, I get 2 moles of H2O out. And these are what are referred to as the stoichiometric equivalents to each other, are equal to each other. And what that means is, obviously, it does not mean in terms of numbers. So obviously, 2 does not equal 1. But what it means is they are equal to each other in terms of proportion. So it's kind of like when you bake, you got to put so much flour in, so much chocolate chips, right, to get your chocolate chip cookies that you make. And that's basically what this stoichiometry is. And this reaction was saying is we got to throw like 2 moles of H2 with every 1 mole of O2 to produce that amount of product. So it's sort of equal to each other in terms of relationship or proportion. And from each of these sort of conversions or equivalents, we can write 2 conversion factors, just like we could do with conversions. And for example, I'll take this guy up this way. We could write from that relationship that we could say that there are 2 moles of H2 on top and 1 mole of O2 on the bottom. Or if we needed it the opposite way around, we could say there is 1 mole of O2 on top and 2 moles of H2 on the bottom. We could also write 2 conversion factors for this guy. And we could say that there are 2 moles of H2 on top, gives us 2 moles of H2O on the bottom. Or again, we can flip it around if we needed to, 2 moles of H2O on top and 2 moles of H2 on the bottom. And lastly, for this guy here, go this way, we could also write 2 conversion factors. We could say 1 mole of O2 on top gives us 2 moles of H2O, or 2 moles of H2O give us 1 mole of O2. So from this one equation that we have up here, we actually can have 6 different conversion factors. And these 6 different conversion factors you obviously would not use in one problem, but you would use probably one of them in a particular problem. And the reason we need these conversion factors is because in these type of problems, they typically will give you information about one of the species in the equation. So for example, in this one, they'll say, hey, you produced 2 moles of H2O. But you're not actually interested in how many moles of H2O you produce. You're interested perhaps in how many moles of O2 that you started with. So you need a conversion factor to go from H2O to O2. And instead of looking it up in a table like we do for most conversion factors, the place that we could get the conversion factors actually comes from the balanced equation. And this is why the balanced equation is really important, because it will provide you the correct conversion factors to do a calculation like that. So in that sort of example that I just did, if we were to do something like that, so let's just say we said, hey, we produced 6 moles of H2O. We want to know how many moles of O2 would that be. We could use these conversion factors to do a calculation like this. So what we would do is we would start with our 6 moles of H2O. Again, we're not interested in H2O. We eventually want to get to O2. So looking at the equation, we see this relationship here that there are 1 mole of O2 gives us 2 moles of H2O, which means we have a choice of these 2 conversion factors over here to use. And again, those conversion factors come from the equation. There's no calculation, just the coefficient. We obviously are not going to use them both. So using dimensional analysis, since the water is on top, in order to get rid of the water, we would want to use the conversion factor here on the left-hand side, because that means I would say there are 1 mole of O2, again, coming from the balanced equation, gives me 2 moles of H2O. And this is really the big stoichiometry part, the part that people have a really hard time with, is right here. This is the big stoichiometry move. And it really is just a conversion factor. And what that's going to do is cancel out the moles of water. And now we've gone from moles of water to moles of O2. Going to attempt it without a calculator. I'm going to give it the college try here. 6 divided by 2, I'm going to go with 3. And that's going to give us 3 moles of O2, hopefully. If I'm wrong, don't tell me. All right, we're going with 3 moles of O2. And that is what a basic, very simple sort of stoichiometry is. And really, all stoichiometry problems are really just like this. They may just have a few more steps, which we'll talk about, obviously. But they're basically what stoichiometry is using a balanced equation to come up with some conversion factors to allow you to go from one thing in the reaction or equation to something else. And again, it all starts really with that balanced equation. Any questions on that? Okay, so scribbled a lot on that page there. So when we talk about stoichiometry, these are the common questions that we oftentimes will talk about. Basically, if we know how much reactants we started with, we could do a calculation to figure out how much products is produced. We also know how much products we produce. We could do some calculations to figure out how much of the starting material are the reactants that we started with. And when we talk about units and stoichiometry problems, whoops, come back. The units can be a lot of things. They can be moles, they can be grams, they can be liters, and we'll get into that when we talk about gases. They can be other units. So commonly in this chapter, it's really grams to moles. So a reminder, if you're going from grams to moles, conversion factor we use for that is molar mass from the periodic table. Don't miss that a little bit later today. Yes. And again, the molar mass, right, is grams per mole that you get from the periodic table, and you essentially can use that as a conversion factor. So a lot of times when we start these problems, you're given information in grams. You typically then need to convert the grams into moles. You then typically need to do the mole to mole relationship from the equation, like we just did in that previous example. And a lot of times as well, after you do this step, you'll be in moles, and then you need to convert moles, usually a lot of times, back to grams, which again will require usually the molar mass again. So a lot of times in these problems, you'll have to use the molar mass in the front of the calculation. Then you'll also have to use it in the back of the calculation as well. And obviously, when we get to other things like gases and other chapters, you'll use some other units. But this mole method is basically where we use that balanced equation, and we use the coefficients as the mole to mole relationship. And that allows us really to find a conversion factor to use in a calculation. Questions on that? Okay, so I'm going to stop there today so we can talk about a couple of things and then give you a little break and so you get ready to take the exam. So first thing I did, I think I remembered, I hit all the buttons there. I moved all the pre-labs to their correct days. So again, a reminder, we basically, starting with the lab today that was scheduled on the schedule for today, which was flame test, I believe, we're just going to move everybody down a day. So we will do the lab for flame test on Wednesday, and the pre-lab will be due obviously for that on Wednesday. And then on Wednesday, it was supposed to be the lead iodide experiment, which would then be moved to Monday, along with the pre-lab, which would move to Monday. And then I think it's a gas experiment that was scheduled for next Monday that has been moved. We'll move it to next Wednesday. So again, on that next Wednesday was a no lab day, so just kind of drops into that spot. So just move all the experiments one day back and or forward, I guess, and the pre-labs have already been adjusted for those guys. So again, on Wednesday, make sure that you do the pre-lab for the flame test again before lab officially starts, 12 o'clock. I think you got to on that. Any questions on the lab part? Okay, now the exam is coming up. It is locked. It will be available right now. It will be available starting at 12 p.m., which is our normal lab time. So got about a half hour or so to relax, whatever you want to do, get yourself sort of prepared. A couple of reminders when you take the exam. It is going to be done on the Canvas site. So you do need to obviously log into our Canvas site. And when you go to the module section, you'll see one that says links to exam 2 or taking exam 2. And there will be a bunch of stuff on there. There will be the academic honesty agreement, which again, you need to read and sign. So I did 2 ways. You can either print it and sign it and upload it with your file, or if you don't have access to a printer, or printing is sort of a problem for you, I made sort of an electronic version of it, which you can just kind of electronically sign by typing in your name and your initials on it and submitting it. In order to get to the electronic one in this module, when you take the exam, you have to do each of those steps in order. So you still have to open and view the PDF file for the agreement, and then that will unlock. That should unlock the electronic one if you want to use that to sign. Or again, you can use the paper version of it and upload it. You don't have to do both. So if you did one, don't do the other, but you do need to do at least one of those agreements. Either need to be signed, either the printed version or the electronic version. Once you've got through all of that, you then will, the link for taking the exam will be open and you can start. Make sure that you do read all of the instructions. So I apologize for all the instructions, but I try to think about everything or every question that you might have. So I try to write every sort of answer that I could think of as I was sort of doing it and going through it. I think I probably covered most of them in the instructions, but just a few highlights of some things just to remember. Make sure that you are prepared to take the exam when you start, okay? Because once you start the actual exam, when you hit the little button that says start exam, the timer will kick off. So you have 135 minutes to take the exam. Now, when you click it, it will start counting. Even if you click away from the page or whatever it may be, you could still come back to it. So if you do happen to click away, for whatever reason that may be for, or accidentally, you could go back to the module section and click on the link, and it'll tell you resume your exam. When you resume your exam, your timer will still be counting down for all that time that you were away. So you want to make sure you have everything. So that would be a calculator. That would be some paper to work out the problems that have work associated with it. Hopefully everybody seems to be able to upload their labs and stuff like that. So whatever method you use to upload your labs, you can use obviously to upload your work as well. Any question on that part of it so far? Okay, so once you start the timer, you can't, like I said, stop it or anything like that. So make sure that you're ready to take it. Now, there may be a problem where you may want to enter the answer in scientific notation. So if you enter the answer in scientific notation, you will use the E. So you'll use, for example, and there's an example of this on the exam that shows you, but if you want to write something like 1.25 times 10 to the 3, the way you would type that in is 1.25. You would actually use lowercase e, not capital, but lowercase e, and you would hit 3. So the E would stand for the times 10 part of the number, okay? Now, as odd as it is, if you do enter something in scientific notation like this, what Canvas will do is convert it into a decimal, yeah, just by itself, yeah? So even if you type it in like that, it probably will convert the number to a decimal, and that's okay. So I'll just write that right there. That is okay, yeah, it'll be okay. But what you should do, if that is a problem that has work associated with it, then on your paper where you show the work, you should obviously record the proper number of significant figures. If you want to write it in scientific notation, you should write it in correct scientific notation. So that's one issue that comes up. So don't freak out if you put a number in. You don't necessarily have to on all the problems or any of the problems, but there might be a problem where you need to put it in scientific notation. It will convert it out for you, so it's okay. Now, just make sure you do it correctly, when you turn in your paper. Secondly, in terms of entering answers online, you do need to enter answers for all the questions if you want points for those questions, obviously. You should not use units. So do not use units, just enter the number. So anything that is a number answer, no units, yeah, for number answers, yeah. So online, just enter the number, but just like I was talking about a minute ago, on your paper that you're going to show the work, make sure that you do have units. So on the paper that you show the work that you're going to upload, make sure everything is set up properly, dimensional analysis, units, significant figures, and all that kind of stuff. But for entering answers online, because it is a computer, it just enter the number, no units involved. Any questions on that? All right. Another thing that might occur when you open the exam and you take it, that you are given two things. You're given a conversion sheet and you're given a periodic table. They're the first two questions that you will see. They're not really questions, but they're the first two slides that you'll kind of see. By the way, when you do open the exam, you will be able to see all the questions at once. So you can go work whichever questions you want in whatever order. The very first two things that you'll see are two sort of questions that are actually conversion. So one is conversion factors and one is a periodic table. Now, when I posted those as questions, they were posted as sort of pictures. And sometimes people, when they log on with their internet and their browser, might not be able to see the question, to see the periodic table or the conversion sheet. So if you happen to be in that situation, I posted in the module section, right where you get the exam, a PDF file of the periodic table and conversion sheet. And that's the exact same periodic table and conversion sheet that would be on the exam. So if you open up your exam, the first two things, you can see the periodic table and conversion sheet, you're good. If you open it up and it has like a broken picture sort of symbol and you can't see it, then you could click over to the module section. You could download the PDF file and you should be able to open it up and kind of see the periodic table and conversion sheets, okay? So in case that happens, that's what you should do. Any questions on that? The exam has not been posted yet. Everything will be available starting at 12 p.m. Yeah. So starting at 12 p.m. it will be available. The exam and all the stuff. Yeah. So got to wait patiently until lab time starts, I suppose. Okay. Other questions on that? Okay. Now, in terms of submitting the exam, just so we're clear, yeah, you could use any paper you'd like. It's as long as I could read it. So again, when you're doing your work, the question was, can you use lined paper to show your work? That's fine. You could actually use any paper you want. Again, the important part is just try to make sure it's clear and that everything's labeled in terms of what question you're answering, the units and all that. So, it's not kind of all over the place. So try to make it organized as you're doing the problems. So I clearly know when I look at the work that's for, problem number 2, or that's for problem number 3. But you can use lined paper if you like. You can use plain paper, whatever you got should be fine. So technically speaking, you're supposed to do it before the exam, the signature on the agreement. So if you do the electronic one, you can do it before. If you decide to do the printed version of it, I'll assume that you abided by those rules and all that, and you could sign it. But regardless, I just need it signed. So again, if you do the printed version of the honesty agreement, just make sure you do sign it and you do upload it with your work later. If you did the electronic version, you don't want to have to worry about printing it out. You could just do the electronic version, and that's good enough for me as well. Other questions on that? Okay. Now, in terms of submitting the exam, like I said, there will be one button at the very bottom of the exam after the very last question. That is the submit button, and that submits the entire exam. So do not hit that button until you have completed the entire exam. Okay, so only hit the submit button when you're all done. Yeah. And all done means that you've answered every question that you want to answer. You either entered an answer for every question, you clicked whatever you needed to click, but do not hit the submit button until you are all done. If you hit it before you have answered all the questions, it actually will put up a little warning that says, are you sure you want to submit this? You've left like 5 questions unanswered. So that hopefully should also tell you not to do it if you have questions you haven't answered. But again, only submit the exam once when you're all completed, and that will submit the answer. That will submit the exam to me. It will probably also give you a score at that point. Remember that for questions that do have work associated with it, I am going to try to go back and give you some partial credit where I can. So your score may change based on, may be different than the score that you see. My guess it would only go up. But I guess that you could think of that as your worst case score if you didn't get any partial credit, but hopefully you would. But it will probably give you a score at the end. But again, that's obviously before I had an opportunity to do any type of adjustments and stuff like that, just so you know. Any questions on that? In terms of the work, not all questions need work shown. So I believe I labeled the questions that need work in red. Right at the top of the question, it will say, you need to show upload work for this one. And the ones that are in blue at the top of the question will say, you do not need to show work. So again, you only need to show work for the ones that say you do not need, you do need to show work, is the ones that you have to show the work. Any questions on that there? Clearly, as we talked about before, yes, this is a closed book, closed notes, closed, don't talk to others. There are different versions, all that kind of stuff and questions. So make sure, obviously, you do the right thing. Again, the PDF file of the periodic table and everything will not be up until exactly 12 o'clock. Yeah. So hopefully we'll be done for here. I gotta go click a button and then it'll all be available for you starting at 12 o'clock. Okay. And you'll be able to find all that stuff. Again, your timer will not start until you actually start until you actually start the exam and click that button like I want to start the exam. Yeah, so when I at 12 o'clock, you will go to the module section and you'll see a module and it will be titled Taking Exam 2. And the first thing that it will say is the academic honesty agreement, the PDF file. Then it will say the academic honesty agreement, the electronic version, if you want to sign it. Then you'll have an opportunity to take your exam. Once you have submitted your exam, the link for the place where you could upload your work will appear in that same module section. So you can use that link to upload your work after that. So you have to kind of do all these things in order. And the reason I did that is so hopefully nobody misses doing anything. So you have to kind of run through that module in order. And after you have submitted your exam, then the link for uploading your file will appear in that module that you could click on it and then you can upload it at the end. Okay. Because I'm assuming nobody's uploading until after they submit their exams. So that's sort of the last thing that will open up. Other questions on that? Okay, so a couple of things on that. And like I said, individual work. Now let's talk about the time limit. So you have, I think I scheduled it starting at 12. You can take it from any time between 12 and 4. It's kind of your window to take it. I would highly recommend you take it starting about 12ish so you do not run out of time. So if you take it around 12ish, you should be able to have your full 135 minutes. But just so you're aware, for some reason, and you should not do this, you should actually start taking it around 12, is if you start, say, for example, at 3:30 and the cutoff time to submit the exam is 4 o'clock. When you start at 3:30, you will only have 30 minutes. It will not give you the full amount of time. So make sure that you do start early enough. Again, most of you, all of you are here, start around 12. You don't have to worry about running out of time or anything like that. But just so you know, if for some reason you decide I'm just going to wait, not a great idea. If you wait too long, you will not get the whole 135 minutes to take the exam. So I would get started around 12ish. Again, you don't have to start exactly on 12 on the nose, but in that ballpark, if you start, you should get the entire time. But if for some reason you decide to wait towards the end of the availability time period, and it's less than 135 minutes until that time, you will not get the whole time. You will only get whatever time is left. So for example, if you fell asleep right now, didn't wake up until 3:55 and you decide to take your exam, you would get 5 minutes. Yeah, so don't fall asleep. Yes, make sure you take your exam pretty much about 12ish and you should be fine. Any questions on that? Okay, other than that, I think that's most of everything in terms of the exam that I could think of. Like I said, there's a lot of instructions, both before you start the exam, and then in each question. Make sure that you do look at each of them. Some of the questions, when you pop it up, if some things are off the screen, you may have to kind of shrink down the kind of view, zoom in, zoom out, so everything could be there. But you should be able to see everything. It was all built through Canvas, so it should all work pretty well through Canvas. Again, both the periodic table and conversion sheet module and the module to take the exam will be available starting at 12 o'clock today. If you have any questions during the exam, you could email me. I think you could actually just through Canvas go to like the email fill thing and shoot me an email, and I will try to answer the question if I can. Like normal, I cannot answer any questions in terms of content or how to do the problems. But if you have maybe some type of issue or something like that, you could email me and I will do my best to get back to you as soon as I can. But like I said, other than emailing me, you really shouldn't be anywhere else searching around or anything like that. Again, do the right thing. But if you do have questions, you could ask me and I'll try to answer or get back to you that way. Any questions or anything like that? Okay, so I will just say then, good luck. Yes, again, make sure that you take it around 12ish, at least start it around 12ish so you don't run into any issues around running out of time or not getting the full amount of time. I tried to write the exam like a normal exam that we would take in class. So it is sort of structured as best as I could do online to look kind of like the first exam that you took. Now, in this one specifically for us, there are some Lewis structure questions. So obviously you cannot draw those online. So for the Lewis structures problem, you will have to draw your Lewis structures, right, on your paper. So make sure, obviously, for that one, it is clearly labeled and much neater than what I just scribbled on the screen there. But the rest of that problem, I think you should be able to answer online. So for sure, the Lewis structure one, you need to make sure you actually draw the Lewis structures with the correct number of bonding electrons, non-bonding electrons, all those electrons shown on your paper. Make sure you do label it. The rest of that problem, you should be able to enter answers. Remember, lastly, that if you do not enter an answer online, I will not look at your work. So all the work that you show on your paper should match the answer that you have online. And you should also write the answer in addition to the work on your paper with the proper number of sig figs and all that kind of stuff and units. Any questions on anything? All right, so if there is none, I'm going to end it. And then at this point, in about 10 minutes or so, 15 minutes, everything will be available for you to start. And you can then start the exam and upload your files and all that good stuff. And we will meet back here on Wednesday virtually for our next lecture. All right, if there's no questions, have a good one. Good luck on your exam. And remember, flame test on Wednesday as well is the experiment. I'll post that up shortly. All right, I'm going to officially end our meeting here. And have a good rest of your day.